Hi everyone, thank you so much for joining us. We are very excited to share with you today. So our project is benchmarking starter speech against automatic speech recognition models. It's a long title, but we'll get into all of the subtopics briefly. First, a quick introduction of our team. First of all, shout out to our PM Anna. She's been amazing. And my name is Ishita. I'm a CSN Math double major at UMass Amherst. Hi, I'm Nikhila. I'm a rising senior and at UMass Amherst, majoring in computer science and mathematics.
Hi, I'm Logan, studying at Olin, majoring in computer science.
So our client is AImpower, AImpower.org. They believe that technology should and needs to work for everyone. Their mission is to research and co-create empowering technologies for, with, and by marginalized communities. Tech should be inclusive. Okay, so 50% of our title was automatic speech recognition models, or ASR. So what are they? It's a suite of machine learning algorithms that can take in audio data and convert it to text, convert the spoken words in that audio to text. ASR models are something that we use in our everyday lives, with Siri, Alexa, and whatnot. So how are these models able to convert the audio to text? Because they are trained on a large amount of speech data. But the problem is, majority of this data is comprised of people speaking fluent speech in their respective languages. So these models work fine with it. But we are excluding a large community of speakers that have stutter speech. Stutter speech is a speech disorder that interrupts the normal flow of speech due to involuntary repetitions or interruptions. Globally, 1% of the population has stutter speech, which amounts to about 80 million people in the world and about just 3 million in North America. So, since these models are so widely used, it's imperative we make them inclusive to everyone. We get so frustrated when we ask Siri for something and it just goes like, I didn't quite get that. Here's what So imagine how difficult it must be for people with stutter speech. So that's the kind of problem that we're trying to solve through this project. Yeah. So first we'll give you an overview of what our data set look like and what we work with. It's in Mandarin. So our entire data set is in Mandarin. It's not in English. So this was a challenging project to navigate. But yeah, it was a great learning experience. That means great in Mandarin, and I verified that with David, who is a Mandarin speaker. Yeah, so we do have audio files of people with stutter speech speaking in Mandarin, and we also have some text files that have the ground truth transcriptions of what was being spoken in the audio files. So this is our basic structure of the data set. We do have two different types of audio files. The first one is voice commands, where the participant is speaking to Siri. And the second is conversation, where the participant and moderator are speaking with each other. And in this case, moderator is a client. So they, AImpower.org, work very hard to make this data set. For the text files, this is how this is basically how each line of text looks like in that true transcription column. It's actually Mandarin, but we are presenting it in English for ease of understanding. As you can see, there is different symbols in the sentence. So in fluent speech, the sentence would be pronounced as, I am Xiaoming, I live in Beijing. But these different symbols sort of tell us how the sentence was actually spoken by a person with stutter speech. So and they represent different types of stutter. For example, square brackets mean a repeated word, so word level repetition. So this person repeated I am while speaking the sentence. Second, so P means a prolonged sound. So the person prolonged the M sound while saying the word am. B means a block, so there was a block between these two words, shall, block, may. I means an interjection, so any sort of between a word, that's an interjection. And lastly, R means a sound level repetition as opposed to the word. So the person repeated the B sound while pronouncing Beijing. So that's how it was actually said in the data set and the audio. And this is the Mandarin link. This is the actual link, what was present in the data set.
And we want to introduce ASR models that we use for our project. And there are many ASR models out there like Whisper Tiny from OpenAI, Wave2Back from Azure, Facebook, and Azure from Microsoft and Google Cloud. And we also included VNet Speech in our candidates of models for because like VNet Speech is specialized in Mandarin.
So far, we've learned a little bit about what the data set looks like, what content it has, and what ESL models are going to set up. But you're probably wondering, wait, what problem are we trying to solve? So, in this project, we're trying to test the speech recognition models to see if we can accurately transcribe stuttered speech. In much simpler words, we're trying to see if the speech models can convert audio files that have stuttered speech to text. So now we'll walk you through the process of how we sort of achieved that goal. So our our aim was to compare the true transcriptions that we talked about with the text generated by the ASR models to test them how well they're working. So we sort of followed two different pipelines to prepare these text files for comparison. For the text files that we mentioned before, we just did some basic cleaning. We removed all the annotation symbols and we removed the punctuations and got the text file for the two transcriptions. For the audio files, we passed the files to the ESR model. We did some cleaning on the raw text. We removed anything that was unexpected. And that's how we prepared the text file for predicted transcripts. And then we just ran several evaluation metrics on both of these files to compare what the error rates are.
So for evaluation, we used 6 different metrics, and for this presentation, we're gonna focus on the most widely used metrics, which is word error rate WER. And it measures the percentage of words that are incorrect compared to the reference, and the calculation is done by taking into account the number of words that were inserted, deleted, and substituted. And the lower error rate, WER score, means the better performance of the model. So for the results, we have 3 key findings that we want to share. So this graph shows each model's performance, and we can notice that VNet performed the best among all the models since VNet was trained on a massive amount of Mandarin speech, which makes this model specialized in Mandarin speech, leading to the best performance for our dataset, which is also in Mandarin. And also we can compare between Whisper Large and Whisper Tiny. Even though they have the same basic structure, the performance, there is a big difference. And it's because of their difference in number of parameters. So Whisper Large has much more parameters than Whisper Tiny, and more parameters in ASR models means it has larger capacity to learn more information, leading to better performance of ASR model. And this graph shows the model's performance by each stutter type. And we can see that word level repetitions, which is represented by WR, and sound repetitions, which is represented by R, they have the highest error rates in contrast to interjections, which have the lowest error rates. So our hypothesis behind this result is that interjections are are pretty common even in fluent speech in contrast to repetitions, which is pretty rare and less common than interjections. So that might lead to the higher error rates that might make the ASR models more challenging to process the speech with repetitions than it was with interjections. And the last key point we want to make is the difference in performance by speech category. And as we mentioned before, there are 3 different categories in our data set: participants conversation, moderators conversation, and participants voice commands. And as you can see here, voice commands have the highest error rates. And this might due to the voice commands shorter audio length. So voice commands tend to have shorter audio length and less number of characters per segment compared to the conversational speech, which made the ASR models to comprehend like more challenging, and this last number of characters provide the ASR models with less context, which might resulted in more errors. And comparing between participant speech and moderator speech, as you can see here, the participant speech has twice as many stutters as moderator speech, which might result in more errors in participant speech.
For the entirety of our project, we obviously overcame many challenges. The first one being, which we repeated multiple times, our entire data set is in Mandarin. And they're all non-Mandarin speakers. We had a hard time trying to figure out if the experiments that we were performing were working or not. So we relied on GPT-4 translations. So we prompted the GPT-4 to translate our entire generated transcriptions to English and then perform sanity checks and manual. And the second challenge was hallucinations. I know it can get a little confusing and sometimes hard to pronounce, but hallucinations means that AI models sometimes can create or generate stuff or make up stuff that wasn't there in the original audio. So some of the examples of the hallucinations can be, you can see an emoji right there. So Whisper Tiny generated an emoji which was supposed to be a speech to text translation with an emoji, which is quite funny. And then we also found non-Mandarin text, which was in French, Persian, and English, and so on. So in order to tackle hallucinations, we removed our data from non-Mandarin characters. And lastly, our data set was quite huge, and we needed multiple libraries to run all these transcription models. And the models were also pretty big, and we were running them on more than 70 hours of audio files. So to make our lives more easier, we moved to Boston University's shared computing cluster. And then also we learned how to do batch jobs, which was quite fun to learn. And moving to conclusion, as you can see from all the results, the models performed quite poorly on stuttered speech. You can see that there was a direct correlation between stutter count and the performance of the model. The more the stutter count is, the poorly the models performed. Having stutter and navigating in this world can be quite challenging as it is. And on top of that, having to having to be excluded from accessing all these technologies can be quite frustrating. People who have stuttered often experience significant barriers when accessing voice activated technologies, and then which affects their ability to perform daily tasks, communicate effectively, or even as easy as accessing basic information. So developers need to create more inclusive technology and make sure that each and every one of us can use it and have equitable access to all the amazing advancements made in this field. Some future steps would be, since most of these models are trained on fluent speech, there are more biases that are being created. So if we collect stuttered speech from various languages and demographics and then train these models on that data, we can we can create a diverse data set which will give better results. And lastly, it's also important to fine tune these models and also improve their performance. And from all the results we found, we aim to publish them and integrate them on our client's website so that more people can see it and raise awareness on this issue. And hopefully, technology becomes more inclusive, and one day we'll all be able to equally access it. Thank you.